welcome you all here to this webinar. So what I'm going to be showing you today is concrete design. Concrete ground beams, concrete pile caps, and concrete rafts. So we'll be using the master frame together with the concrete, either as part of building design suite or as power pad or standalone. Doesn't actually matter, the mechanics of it is all the same. Naturally, the rafts doesn't actually come into the power pad bit, but we will cope. So I'm just going to close all that down and come straight back into the master series. I am going to go in and look at my ground beams first of all. It's very overlooked in the design of concrete ground beams. It's very blasé for small projects, for housing, for whatever on piles, where you need to do ground beam arrangement. And this is my arrangement of ground beams, and you can see that I have a lot of beams and piles all over the place. I also have some nice cantilevers, because for whatever reason I decided to put the piles here rather than at the ends, and everything is straightforward. Now, it's not a webinar on how to create frames, it's a webinar on the concrete and design primarily. So what I want to go through is, first of all, the loading. And I want to look at how you would apply member loading. Normally, you'd go along and you'd apply member loading to that member. And then you'd apply member loading to this member. And to get these two alternate and different, you'd apply different load groups to each one. But I am not going to do that. Every single version of the master series, other than the very tiniest frame analysis, has area loading. So I'm going to maximize my use of area loading. So instead of individual line loads, and I actually have put a line load out here because it's outside the areas. So I have put a wee dead load here and a wee dead load out here. But everywhere else is going to be area loading. So let's go back and look at area loading. And loads, floor, and the default on level 1 at 0 is going to be a 200 slab. It's going to be a superimposed additional load of 1 and additional load of 2.5 for live load. I'm going to put no other loads on. So with the 200 slab, it'll actually take the self weight of the slab as well. So that's your first stage. The next stage is very straightforward, is adding the panels. And what I've done is I've added all of these panels, and I've added them as spanning in the x-axis. But what I then did was I overrode these ones here to span in the z. So if I just delete this for a second and add a new one, and then just window all the frame, and there we go. So we're all spanning in that one direction, be it X or be it the Z. In my case, I'm going to say X, but what I'm now going to do is I'm going to make local changes here, and I'm going to change this so that the span is now in the Z, and then I'm just going to say copy that onto that, and that short one. So everything else spans left to right on your screen, but those 4-5 panels span top to bottom. All the loading is as we defined, except we've applied a whole multitude of additional line loads from the walls, because that's what ground beams are really all about. They're not really about carrying slabs, although they do. Mainly, we end up having walls on them as well. Otherwise, you wouldn't need to do an analysis. So we've got our external walls with our dead and live loads on it. We've got our inner walls. We've got our minor walls, and we've got some additional loads coming in from the roof above. So I've put quite a few loads onto this, and we will see when I ask it to draw it up that it actually does give quite an extensive set of loads. So dead loads, we're talking anything up to 85 kilonewtons in certain areas due to the heavy loading and addition of loading in 2 directions and things. So quite a few loads, all calculated automatically for you, particularly for the slabs. So if I stretch a slab, it'll just update itself. The live loads might be a bit simpler to see. The 23s and the 52s coming in from the heavy loads from above, and then the shorter lighter loads on the outsides. And I don't claim that this is all 100% accurate. I've made this up as a demonstration. But what we haven't got here is the ability yet to pattern the loading from load case, from member to member. And that's important because we are in a continuous situation. So if I go to floor panels and look at alternate load patterns, what I now do is I designate beams to be either D1 L1s for our loads or D2 L2s. And it really helps if I see the supports at the same time. So we can see all these have been designated as D1s, L1s. So we'll get, if we go for D1, this will be D2, D1, we'll get a max, min, max, and a min, max, min. And then if we look at the opposite, we see the other direction. And they're just very simply just applied and removed with the click of the mouse as normal. And luckily we can draw both sets together and see all of them arranged out. That member doesn't exist, it's just a dummy member to allow us to span in that direction and then that direction for that portion. So everything is one-way spanning. That's all my loads done. Now moving forward quickly. If I look now at my loading cases, my loading combinations. And combinations, I have all spans loaded, and the D0 is the self-weight of the slab, and so that's all spans loaded, maximum. And this is max min now. In the Eurocode, which we're using, you could have got away with only a D1 for all the dead loads, but it's easier to work with than two separate values just for completeness. And then they'll reverse minimum, maximum. And then we have the serviceability equivalents of those and nothing else. And the nice thing about the MasterSeries is you can either store those and pull them in again as importing from file, or you can even store them as a set of defaults and import them as a set of defaults for you. In my case, I just pulled them in from another file. So let's go and analyze. And what I'm going to do first of all is I'm going to set up one or two global options. I'm going to turn off a little trick that we will learn about in a minute and do a static analysis. Very straightforward, and it could just be a grillage analysis because it is planar. Now, let's look at our results and our graphical results. And we probably don't need to see those in green, so I'll just tell it not to draw them by section. And there we go, bedding moments. And I can just scale up the number of hatches. And what we're seeing here is we're seeing at the ends hugging moments, and strangely enough, a kick down here. And if we look at these two values and just turn off measure, we have 6.2 and 16.5. Well, I can tell you what they are very straightforwardly. The 16.5 is the torsion in this member to give the moment here, and vice versa. So if we went to torsion, we would see that the two values swap around with each other to work hand in hand. And we can go ahead and design for that. And the code tells you, yeah, design for all the forces that are applied. But it also says that if you want to, you can ignore the torsion in beams, provided it's stable and designed accordingly. So what I'm going to do is going to come back very quickly, and instead of going pin, pin, and then suddenly having an instability, I'm going to use a wee trick. And the wee trick is that under global options, you can say ignore stiffness. Now, the one area you need to be careful is if you had a cantilever that was coming off another member that was relying on its torsional stiffness, then you could have a problem. All of our cantilevers are continuations of other members, so they don't have a problem with stability being provided by torsion. So analyze, static analysis, very, very quickly. Grillage again, results just for 1 second. And we will see our bending moments without our fixed end moments, just pinned as you would have done by hand. Continuous throughout the length and then pinned. Obviously this cantilever here is causing a little kick around. But if you look at one of these, and I'm just going to pull the hatching down because the more hatches we have, the smoother it is. And we see that we're looking at ultimate, so we're looking at a max min, max. If I go to max min, you'll see that this moves and then a opposite min max. Now, because dead loads are a significant part of ground beams, we don't get as much of a changeover as you would have thought. In some of the areas, we will get more of a changeover. I think with this heavier load on this member, we should see a difference. There we go, and though. So you actually see that we were actually nearly getting a point of lifting up on this rather than sagging. So we're getting no point of counterflexure. And we can look at the ultimate cases as an envelope, and you'll see on any particular set of spans how the effect of the different conditions. So maximum, minimum give us a higher sagging moment here. So it's always important to do your pattern loading. So that's that done. Now, let's walk in and do our concrete design. Design concrete beams and columns. And here we come in with our design setup. And I've been in here before, and it would just do this automatically anyway. But what I've got in here is some basics. So let's look at our auto design. We're going to use anything from 6s to 25s, a bit extravagant, and from 2s to 6 bars, and from 100 to 300. So I've opened it up, and I'm going to put in a 10% reserve, a little extra load factor for myself. Covers, we're going to go for 50 bottoms and 35 top. And curtailment, we're going to just go for standard detailed. And we'll have bob bars at the ends of spans. And everything else is pretty straightforward. And if we look, EC 8666, deform type 2, 500B deform bars. And I'm just going to say OK. So it's going to run through and apply that to all of these. And you're going to see when I do an auto design on this, it's going to suggest, in fact, 612s and 612s. That's ludicrous. So really looking at the width of my members, which are 350 wide by 500 deep, and it chose them to be slightly deeper, so I didn't need to get an extra link in there. I think a wee bit of extra concrete is cheaper than extra links and all the fitting times and hassles. So what I'm going to do is nip back, refine this, and say no. Let's go for, we could say 3 bars and 3 bars, so never less than 3 bars. And I'm going to say, well, actually, nobody uses anything less than 12s anymore, just for the transportation and moving about. Okay, well, we'll put in 10s and see what happens, and say okay. So if I redesign that, it'll now give me 3 12s, 2 12s and a 10. So we're being very optimized by putting in different bars of different diameters, but they're ground beams. We don't want to get into that fussiness. So let's go back to our table again and look at our auto design and look at our curtailment, and we're going to say 1 bar group per zone. Absolutely makes more sense. I know I'm only looking at a simply supported beam at the minute, but it gives us a focus. So resize 320s and 316s. If I reduce that using the left and right mouse button down to 316s, it fails. So yes, it would need 320s in the bottom there. Maybe 4 or 16s would have done the job, but we have elected to keep it simple with a 3 bar arrangement. I could actually override that and just add in another bar or 2 if I wanted on the bottom, just to make that more economical. So I've got my configuration. When we look at our spans here, we will see that we have similar arrangements. I'm just going to go and auto size everything, and then we will play with it to see what happens. And it runs along, And one of the things you find with ground beams is the spans can be quite short between piles, and because it's domestic between locations. So let's have a look, and you'll see that we've got these 12s and 12s with the 12s lapped. So there's a lot of lapping going on in these short-ish spans. And one of the things we've found is that rather than doing your traditional support mid-span support, there's another method of curtailing that is actually a lot more efficient in ground beams. So if I go back to settings and go to my beam curtailment, I can choose 2-zone. I will explain this in something in here. So we've got 3 bars, zones. I'm going to resize this one. It's 2-zone. So it laps the top steel in the middle and the bottom steel at the right-hand support, except for on left-hand spans. And that gives me a far more efficient layout. It's not pampering as much to curtail it to the nth degree. So we can see, here we go, we've got starters coming along, lapping here. They're not that long, they're 3 meters long, and then, and again. So it'll make your life a lot easier than it would. You'll also notice when we have this span here, that in here there's little dots, and that's to represent the steel coming in a direction. So it's dropped the steel down on the top to allow it to pass through. The bottom steel doesn't really matter because it's not doing anything. It can be just above. So it's made allowances for those in its design. And that is how simple it is to do your ground beams. And you'll see that, for ground beams particularly, we don't have much in the way of links. 12s at, or sort of 10 2 legs at B8s, so 8mm bars is all you need for those links. And that's very straightforward. Now, stepping back, if I look at this, this is 1, 2, 3, 2.5 meters, and this is a couple of meters, and this is a couple of meters. You could even think, particularly in ground beams, that you might want to push this all into one and just do one set of bars across the whole length. Well, we can do that, and the way we would do that is to create what we call a super member. We are going to go and apply, and we're going to say add that member, that member, that member, and that member all into the one super member. And I think I've just done it twice here. Just going to delete that. Yeah, put this into top view. You're better just a window in one length, the whole of what you want to do. That's now one super member. And if I then just move out of that, go to another member, and back again, you'll see now that it does the whole thing as one length, and it is only 6, 7, 8. So we could turn around and specify very straightforward how you want the bars lapped up. Now I'm just going to drag that across to give it a correct lappage. So very simple. Because of the hugging, we actually do need more reinforcement, and maybe in this instance it might have been more sensible to go for 3 zones, but you have those flexibilities and scopes where you've got very short members together to glue them for curtailment into a more harmonious system. So we might have taken these 2 shorter spans and made them one. Obviously it depends on your lengths and everything, and that is everything detailed. And of course, we've now got a more rigorous set of details on that. So if I go back to super member and highlighting that one, just delete it, and then just come along out of that into briefs and resize, and then resize. I could have actually just done the run. I've done all 3 parts. So it's just looking for 3/16 here, and it says the 3/16 isn't going far enough. For whatever reason, it stops them short. There we go. And we're in here, and we need, our steel needs to be increased. If I'd done it in one go, it would have actually sorted it for me. So that's concrete ground beams. Now, the beauty is twofold. One, we can take this, we can export the whole thing as a DWG or DXF. Off it goes, and I can export the DWG and load it into AutoCAD. So I'm doing it as a DXF rather than DWG, and file exists, overwrite it, yes, with my brand new Rebar. I don't know about you, but every new version of AutoCAD seems to be opening slower and slower and slower. So there's my reinforcement and all detailed, and there's a little jump in depth of slabs here, and it's reinforcing that with the jump in the slab between the two levels, and everything is all good and kosher. To mirror that, we can also print a schedule of all that rebar. And I'm just going to go ahead, do them all, 8666, and off it goes. And it's given me the schedule of rebar that matches that. So very straightforward, very, very simple to use, and very versatile is the concrete ground beams. Now, I'm going to move on, and I'm going to move on to the second of my components. And the second of my components is going to be pile caps. So I'm going to look at, actually, no, it's not in there. If I go to the front screen, I'll be able to see better what I wanted to do. And it was this frame here. I'm going to just take a 2D frame, just for simplicity, for doing my pile caps. And I put some ground beams on it as well, just to get some more extra load onto it. Because the slab's going to be, if it's on pile caps, obviously the slab must be suspended, so therefore it must be getting onto those somehow. Similar process of alternate loading, dead and alive. And if I go into design and into pile cap design, very straightforward. I'm going to say, right, let's look at this. Diameter of piles is 300. The pile working load is 500. And we're going to stipulate a minimum of 2 piles here. So it's got 2 piles, and I could turn around and say, just rotate that through 90 degrees, so it's sitting, not projecting into the other property. So there we go with our piles. Now, what I can also do here is I could suddenly offset it in one of the major or minor axes and give us some additional forces. So I could move it to one side if it was an edge, and offset that, and we would end up with a slight differential in our forces. So our maximum load per pile is 310 service, 408 ultimate net. That's what we designed for. And we can see the variation between the 2 piles because of the eccentricity of the loading. We also have, I suspect, some moments kicking in. There's a small 5 kilonewton meter moment kicking in, and in service there is no moments. So that's my first pile cap, and I'm going to look at it in more detail in a minute. What I'm going to do is I'm going to take this information, I'm going to copy that as a copy to the next pile. There we go. And it's saying, oh, no, not true. So first of all, let's get rid of these offsets. Make it 0 and make it 0. But certainly 2 piles is not going to work. Our pile capacity is suggesting we need more than 2. And I am suddenly going to come back to the first screen and say, well, let's go for 3 piles. So, okay, it's telling us that it's too shallow and we should use beam theory. So maybe we want to increase it, but also looking at the shear plane, it's quite problematic, and we really need to improve our shear through increased depth. So let's go to the pile head and change it from a 400 to 450. And we'll see now that this simple 3 pile cap works. And I can take this and hopefully see if this will work on the next heaviest loaded. And it does. And I can copy that onto the next one, which is going to get quite a lot heavier loading. And it is now not working in both shear and in both directions. The bending's okay. So the shear is a wee bit suspect. Will reinforcement improve the shear? I could take that down and improve that considerably. but in the XX, it's not giving me any benefit going up to heavier. So in reality, if that's the case, we just need to deepen our pad. So let's make our pad, our pile cap, 600 deep, and we could then come down and stick, let's say, rebar 200 centers each direction, or smaller diameters closer together. And taking that one, I might want to take that pile and put that over here, and that's not going to work, and it's not going to work with the loading because it's quite large spans and heavy loads. So we really need to come back and go into at least a 4-pile cap. And 4 piles are lovely because, you know, there's 2 of everything in both directions, and it makes shear a lot better, as well as everything, and bending and everything a lot more simplified. So all spans loaded, you know, coming down through, we can see everything. What's our rebar, our main bar? We'll keep it at those 20s at 200 and have done with it. Now, let's go to the last pile, and I'm going to take this one and I'm going to copy that onto my last pile, and we'll see again I've got a shear problem. Now, reinforcement may not solve it. Let's see if we can come down, and we're within 2%. When we come down to quite a low rebar, you can see at 150 centers we're beginning to get close, but not close enough. So in reality, we want to go up to 500. Now, what you may wish to do is to go back and rationalize all of those pile caps to be the same depth. Otherwise, it doesn't consider it otherwise. You know, it could be dangerous. Naturally, everything detailed out will have the depth of each of those pile caps, but I think it would be much more sensible to have them all. So if I was to go and say, right, this needs to be 600 and this 600, let's make that one 600. Let's make that one 600. And obviously, let's just make that one 600 and that one 600. We now have no conflicts of depths. All the piles can be cut off at the same height, and all the pile caps popped in accordingly. And of course, this one already was rotated at this end, so it's rotated here as well. And that's quite useful. It's also still offset horizontally to the one side, so it's not as far on this side as this side. So I'm assuming that's an external surface, and it wants to keep it a bit simpler. So it's working out all your pile loads automatically for all of this discontinuity. And if I look at my 4, you'll see again it's looking at different loading. And it's looking at different loading in the major and minor. The minor, it's the same, but the major, it's got this moment of 96 to consider and handle, and moment of 135 at ultimate limit state to handle. So it is working away and doing everything you need. Now, the design method has been the strut and tie. We can use beam theory within reason, and we can also go and use the maximum or the minimum of the two. When we're in beam theory, of course, we would like to use deep beam theory. And when we're looking at trusses, strut and tie, we will check our compression zones. So we're looking at all of those for us. And again, whether or not you are of the school that designs for net ultimate or gross ultimate. Gross ultimate's more conservative, obviously. So net ultimate might get things slightly reduced on you. So there you go, that's the pile caps, and it's again very straightforward and simple, and we can again export all of those out to a DXF or a DWG. We can also print schedules on them. So let's just run a schedule through, and here we go. So we've got our rebar all the way ready for us, scheduled and everything, straightforward for you. So again, a very, very worthwhile program. The pile cap program will also work in a standalone mode. So if I was to come out of my frames, there's absolutely no reason why I couldn't do an individual pile cap where I'm stipulating the dead and live unfactored loads. So there's one. and open. And you'll see that it's just a 4-pile cap, eccentric, and its pile capacities aren't big enough. So the working load, well, the 250 piles is probably around about 350 axial load they'll resist. I think it's actually slightly higher than that, but everything else works fine, and it's all checking the punching shear and everything for you. So all good and simple. So that's your pile caps and your ground beams. The next thing I want to look at is your rafts. So let's look at this little slab. Rafts are done using fine elements together with our concrete design component for slab design. So there's my little raft that I've created as an FE surface. If I go into modify geometry and even just go into create, won't matter. I'll get rid of my mesh for a second and I'll show you. We have modeled the downstand beams that we have asked for as being in from the edge of the slab. It does give you a slight advantage, but it's not necessarily necessary to have two sets of lines and everything. We've also got a major wall coming across here and here. There's a third reason for actually putting these lines across. We could do without them if we had to. And the other interesting thing is that I have introduced two columns. Now, there's 2 point loads coming down, and for punching shear, you really need a column above or below. In our case, a column above. Otherwise, it doesn't know how to handle it. So anywhere you have a point load coming onto a slab, you should really be having that coming through from a column of some sort. And I think my columns are just, it's 100 by 100 square hollow section. Loading wise, very straightforward. Let's look at the properties first. Properties, materials, 200 slab, a codified concrete C2530. It's domestic. If we look then at attached beams, all of these beams here are attached beams in the software. All of these will be attached to the bottom. So we only define the portion that's below the slab, not the overall. So it's probably only going to be beams of around 150 deep. So that's going to give you 350 overall depth with the 200 slab. And we're going to assume a 300 flange either side from an analytical point of view. And we will use the flange widths. So we're going to combine all this into our design. Loading, I've got 2 area loads for live and additional dead. And again, just like the other, I've put them in as being alternate load pattern type loads, and we will define the patterns in a second. So line loads from walls on the 2-story and line loads from walls on the 1-story. Internal wall, and then edge walls, that's dead and live spanning across there, dead and live spanning across there, and dead and live spanning across there. The dead and live here is coming down onto these 2 point loads. Everything is alternate loading. And then we have the 2 point loads, dead and live. And then we have the additional wall at the back. And then we're going to come in for additional wall loading. And that's it. So all of those are put in. And we do a similar thing for loads, for area loads. We do a similar alternate patterns. I want, because of this hard point here and hard point here, I want to pattern it so that when this is loaded, this is not, and vice versa. And likewise in that direction. So I've created up 2 load sets, load set 1 and load set 2, to give me max, min, max in that direction, that across the X, the north to south. I've also done the same in the east to west, where I'm going to take it, this is loaded, that's not, and vice versa. Or I could have possibly done it that those 2 would be, but it's up to yourself how you pattern those. I'm now doubting myself for this one. 3, 4. So that's, yeah, we've already done that direction. We were interested in across this wall, maximum here and minimum here. So we've got that all covered. And again, it's just the same for the loading cases, except in these you actually end up with twice the number because you've got to do them in 2 different directions. You've got to do them north, south, east, west. So we end up with L1s and L2s and then L3s and L4s. So let's go and just analyze this and examine. But before we do that, supports, the most important thing. And let's look at our restraints, static supports. I've got a support here that is a pin, but with no vertical. And I've got another one over here that's a horizontal, no vertical. And those 2 supports together stop me having a couple spinning on plan. It gives it X and Z directional stability. What the other thing we've done is we've put in a spring stiffness. Now, spring stiffness or subgrade modulus, number of kilonewtons per meter squared to compress by 1 meter. Quite difficult to ascertain. Luckily for me, I have a publication that I found years ago that gives some very good guidance on values, which seem to work. Most people just choose a value and then see if it gives them the diagram they want. But in here we can see we are talking about bearing pressure. Here we go. Subgrade reaction or subgrade modulus. So loose sand would be from 4 to 16,000 and then medium to dense. So I put in 10,000. So it's a very soft situation. And you can see also if you're into others, you can see if you have a Q value of less than 200, you're 12 to 24. So I'm down at 10, that lowest minimum of those values. So 10,000 telephone numbers. Very straightforward. Let's go and analyze. Static analysis and space frame. So my 12 cases. 3 in one direction, 3 in the other direction, and then the serviceability equivalents of those. What I forgot to say is that for service cases, I told it to use a Young's modulus of 1/4 of the normal to give us our deflections. Here we go, nearly there, 8 cases done. And it did all the meshing by itself, and we also have this little opening in here for, I assume, services to come in, telephone and other things to come into the building. And it's now just doing some factoring and saving back down. Yeah, doing this combined forces, and there we go. So let's look at our results, graphical results. So we're in our finite element program, and we can see some bending moments coming through on the beams. And the beams in this sort of arrangement aren't doing much other than holding each other's hands. That's a wee bit of a weird one. It's you don't necessarily need them that much, but people like to put drop beams around the edges. And obviously here there's a little hard point where it's flexing and then flexing down. Deflected shape, hard to see. With diagram, and we'll see that the whole surface has gone down, and we'll see a big drop here and a big drop there, and quite a drop in this corner below. It's been supported in 3 directions. But that's not really what you need to see. We go into shell elements, and now we get the information we're after. Let's go, first of all, to Y displacements. Put it in top view. Virtually no displacement here, and highest here and here. And because of the gravity of the walls pushing down and the internals flexing up. And that's the classic flexural expect. That's with everything loaded. So let's look at maximum, minimum. That's right, serviceability. We can now see the first pattern and then the other pattern where you have maximum, minimum in the other direction. And of course it rescales every time, so the intensity of red will mean a different thing in different loading cases. But that's all very difficult to work with. What I want to look at is, let's get back to the ultimate. Let's go to MX, the moments in that direction. So we can see that we're flexing here and then we're just relaxing. So this point load, this wall pushing down is causing it the moment here, and then it's just going and relaxing. Bit more different in that direction. The y-axis is doing the opposite. It's doing a bit more of a case of spanning across because it's wide enough. But those are major moments. We want instead the realistic wooden armor moments. So we can see our wooden armor moments, and we can see our wooden armor moments. And that's great. It's brilliant. It's lovely. We can also come along very quickly and say, well, let's look at our top steel. And it's going to give you an idea of what sort of reinforcement you need. And it's telling me here from my idea of reinforcement that I'm probably getting away with 252 quite a lot at the bottom. But I'm not going to waste time on that. I'm going to go straight into the last program that I want to show you, or last module, and that is slab design. So design concrete slab design. And what I'm going to do is I'm going to just get rid of everything. Make sure I've got everything out of here. And we're going to, first of all, look at my defaults. What are my defaults? 500H sounds good to me. 50 cover, top and bottom, yep. And punching shear, if hopefully we won't need it. And basic rebar. 8's at 200, so a 252 mesh. Peak zones, hopefully we won't need them. Strips, we may need them. And it's always going to be parallel to the line, so I prefer it to be perpendicular to the line and to be an additional set of reinforcement. And detailing is all the same. So save all that. So what I'm now going to do is add this basic mesh. Sorry, not punching shear, basic. Add the mesh, and it's now going to say select where, and I'm going to say onto this surface. So it's going to tell me all my failures here. It's not telling me anything over here because at the minute I'm not looking at any results. So let's look at my hugging XX, and I can see failures in the hugging here and here and here and here. You'll see where the edge beams, the beams are, because we're spanning in that direction. In this width of slab, it's the beam that does the design, not the slab itself. And so we would need to strengthen it in here. This is in the hugging. And in the Y, we would need to strengthen the whole of this area and not this. When we get into the, and it's just doing them combined, the sagging. So sagging is your bottom, which is what you would think of as supports. So we can see a little bit across in this direction here and here and here, and a little bit more across this hard point where this wall was coming in and flexing across. So that's where we need to put a reinforcement. So my first thought is go and change everything to 393s and then see what we need to do extra. So I'm going to go back to my basic, and I'm going to change my bottom steel to 10s and my top steel to 10s. And now let's reassess. Let's reassess my sagging YY. I need to enhance it here in that direction on the bottom, and I need to do a wee bit of enhancement around these corners. But small areas of red, like you have a V value here that's red and here, they're so insignificant with everything else that you don't bother to worry about those, and that is actually going to be covered by the beam anyway. So it's really only this we want to strengthen. So what I'm going to do is I'm going to introduce a strip of rebar, and I am going to draw it on this, and I'm now going to say it's going to come from here all the way across to here. I don't know how I got into plan. So there it is, but nothing's happening. And I'm just going to take that and stretch it out to the edge of the beam. And I'm going to stretch this out a wee bit more to here. So default a meter either side, that's fine. But it's not doing anything. It's not giving me any changes in color, and the very simple reason is it's on the wrong surface. It needs to be bottom. And hey presto, my additional 10s at 200 is not working over this. So we need 10s plus 10s. So this is quite a heavily reinforced and flexing component. So I would consider making these into 16s. And it's now working at 97. So 10s plus those additional 16s just laid in between the other bars is all you need there. And those small areas I'm not going to worry about. So let's go back to the basic. Very simply, scan through the different hogging areas. And I still need to sort out this hogging area here. And is that X? I think it's Y. There's a little bit there. And a little bit there. So I would consider putting another strip across here on the top steel as a strip. Or I might go back and just put in heavier basic reinforcement. So let's add in another strip here. And I am going to draw the strip, highlight the surface, get myself orthogonal on that, and then drag it down. You might as well just have it down to the edge and have done with. And it's nearly there, but not quite, as 10s. So we may need to go up and improve those to 12s. And that should now make that work. So that's a parallel. That's actually not part of that proper design check. That's interesting. Did I use a strip? I did use a strip. So it may be that you decide in the end that you don't like that idea. And the easiest is to get rid of that, get rid of that, get rid of that, and to put different rebar in here to here. And we can do that very simply by coming along into the basic. And I can turn around and say, I want to redefine this only on a rectangle. Or, being lazy, I can just put a peak strip in here. And I'm going to, doesn't define it from here. And I'm going to take it to be not square, asymmetrical, which allows me just to say, right, all the way down there, all the way across as a replacement. There we go. Top steel as a new peak zone 1 additional over it. Now, one of the things at the minute is the averaging is you need to be careful in this, and it's not over the full width, but over 5 effective depths is a more realistic design process. So that's telling me that we can use 10s plus 10s. I can then turn around and say, well, instead, let's just replace it and then go 16s or 12s and see what happens. It's just doing all its calculations. I had quite a fine mesh in 1 or 2 areas. And yeah, we're slightly over. So you turn around, you'd say, direction 1, we're going to go for 12s and see what it says on that. Although I'm looking at the other direction, so it's not going to immediately show up the difference for me. There we go, direction. Probably needs 16s because of that heavy load. So jumping from 12s to 16s should give us something a bit better. And there we go. So 12s in one direction, 16s in the other, and that's the solution. That is simpler reinforcement to be applied, but it's really up to you. Do you go for a small basic and then a lot of additional, or do you just go for a blanket additional? So, and again, that can all be spat out as a drawing for you into AutoCAD. And there's a very good video on this, and if you just come back out into the home screen, you'll see that this project was actually done in detail in this video, and that's a very good video to show you how to do that. We have a multitude of videos available to you under resources, and then just go to videos and you'll find all our videos on our website. So it's already 2 o'clock, a very quick run through the questions. Any I don't get a chance to answer, I will come to afterwards. Do you just accept it or design out for torsion? Well, if you remember in my little frame, I ignored the torsion. You can include the torsion and then design for it, and absolutely, it's not a problem. So under analysis, global, we could say include torsion, and then we will get additional steel in our concrete design to cater for torsion. If it's high torsion, it'll start to remove some of the main steel from the capacity design. There was quite a torsion in one of these, if I remember rightly. So you know you've got bad torsion when you suddenly find sidebars. But if I look at one of these and look at the results, you will see that there's a little bit of torsion being resisted. And in our case, it's very unhappy. It needs a lot more in size in links. It's overstressed on the link component. So we would like to see better links, but also it has worked out what the torsional steel is. So we're going to deduct 343 millimeters of steel. That's quite a bit due to the torsion. So yes, you could come along and say Autosize that, and it's now probably got 16s and 20s because of the torsion. So yes, you can design for that torsion. You can put the steel in that you need and keep going, and that's fine. Some people don't. Some people prefer the pinned solution. So we give you the option analytically to do it either way. Can you have a wide beam? The load from walls may be eccentric. Well, yes, you can add in wide beams. In FE, it's not really a problem. The load just applied where it's at. In beams, you can, in the loading component, apply them offset, and you'd have to apply them as member loads and offset them. Why do you have a support width of 200 with beams 350? Well, the beams are 350 wide, but what you're looking at, oh, sorry, wrong button, is this little support here. By default, it assumes 200 wide for your curtailment and everything, and you can put in the width you want for this, and it helps your shear design. The other thing I would say here is that everything is good. You don't need to do a pile cap design on these because normally these are individual piles, and as long as the pile is not less than half the width of the section, then the gross cross-sectional plane shear will cover it, and you won't need to look at the punching around the perimeter. Does the pile cap designer take into account the 75mm tolerance? Well, everything is assumed to be construct it correctly from a design point of view, but certainly, yes, there is a 75 or more allowance on the pile caps for the edges, the projections, and that allows you to have that misalignment. The misalignment in the pile themselves, that's part of your load factors. In the piles, can you add in top steel? Absolutely, you can add in top steel. It's one of the things I kind of ignore because it's not necessary, but yes, I know where you're coming from. Top steel is a health and safety issue more than anything for piles, and either in the linked or the unlinked piles, in this case, we have gone for top steel, provide an upper cage, or we could say, no, we don't need an upper cage, and we end up just with these bars sticking up, which can be a health and safety hazard, wanting to impale somebody, so quite frequently they will pop in a matching upper cage. In Raft Slab Design, how do you deal with soft spots or hard spots? That's a very good question, but if you don't know where they are, that's as big a problem. If you don't know how big they are, that's another problem. The best way of doing it would be to create two separate areas of FE surface, two separate surfaces, and give them different subgrade modulus. Otherwise, you're going to be into 100,000 loading cases with 100,000 different locations of that one square being of a lower grade. I think that's about it. Certainly, if you're interested in trying any of these modules or in getting prices for them, just give myself or Andras a shout. Just send the email into sales@masterseries.com and we'll sort you out. So, ladies and gentlemen, I'd like to thank you all for coming. Have a very happy and safe Christmas. Stay safe.